Hi, everyone. I'm Holly Westfall from the University of California, Irvine. Today, I'm going to talk about a project I've been working on with my advisor, Michael Lee, in collaboration with a local Alzheimer's clinic. So in cognitively healthy adults, memory for past events or episodic memory tends to decline over time, but memory for facts or semantic memory typically remains intact. Patients with Alzheimer's disease display deficits in both episodic and semantic memory early on in the disease. Now, when patients are tested for symptoms of Alzheimer's disease, very often they use these brief cognitive measures, so things like tests of verbal abilities, categorization tasks, or memory tasks. And the data I'm going to talk about today comes from one of these cognitive screens. So I guess I don't really need to say this to this audience, but cognitive science can be used to compare theories of cognitive decline in Alzheimer's patients. And through the use of cognitive models, we can make inferences about underlying parameters that we can't measure directly from behavioral data. So through a collaboration with a local Alzheimer's clinic, we have access to a large clinical data set of patients with Alzheimer's disease. And for this data set, we have the results of a mild cognitive impairment screen, or MCIS, which includes a whole battery of memory tasks, but today I'm going to talk about two of them, a triadic comparison task and then a subsequent free recall task, which I'll describe on the next slide. So for this study, we examined the results of the MCIS for three groups of participants. We had healthy participants, healthy controls, people with mild cognitive impairment, and people who've been diagnosed with Alzheimer's disease. So the control group has no functional cognitive impairment, while the MCI group are beginning to show objective deficits in accomplishing more complex tasks, so things like managing finances. And then the patients with Alzheimer's disease have been diagnosed with moderately severe dementia, so they are starting to show difficulty accomplishing daily living types of tasks, so things like dressing and bathing. The full data set contains over 5,000 assessments from the three groups, but we sampled 100 tests from each of the three groups to analyze for this project. So now let's talk about the tasks. First, the triadic comparison task. So in this task for each trial, patients are presented with three animals, and their job is just to choose the one of the three that doesn't belong in this set. I just want to point out that this task is administered verbally, so not using these really cute cartoons. I just have them here to help me talk about it. So for example, for the words giraffe, elephant, and cow, a person might choose cow as the odd one out. And there's not any right or wrong answer for this task. A reasonable person could choose any one of these animals as the odd one out. So patients don't get any feedback from the clinician. For each participant, 9 animal names are drawn from a pool of 21 animals, and each animal is presented verbally in a triad with every other animal, which means that over the course of 12 trials, each animal name is presented a total of 4 times. And then after a delay in which they complete other kind of unrelated tasks, there is an unexpected surprise free recall task of the animal names. The instructions are just to try to recall as many of the animal names as possible in any order. So in an initial analysis of the data, we looked for regularities that you might commonly find in free recall data, things like primacy, recency, repetition. On the y-axis here is the probability of item recall. And the first thing you'll notice is that there are clear differences between the healthy MCI and dementia group in terms of probability of item recall. In the first plot, we see no evidence of primacy effects for any group. So an animal name that appeared early in the list was not more likely to be recalled than an animal name that appeared later in the list. In the middle plot, we see some modest evidence of recency effects. So an animal that appeared at the end of the list was slightly more likely to be recalled than one that appeared earlier in the list. And these two findings together are consistent with other research involving incidental learning, where you see these effects of recency but not primacy in a surprise free recall task. Another common finding in memory search is that the probability of item recall increases when that item is repeated during study. So what this is showing here is that the more often that an item was chosen as the odd one out, the more likely that animal name was to be recalled. So for the purposes of the cognitive assessment, the triadic comparison task really just acts as the study phase for the surprise free recall task. But the design of the task is really different from a standard study phase and a typical free recall task, making it challenging to model. An appropriate model of free recall would need to be able to account for some recency effects and then also allow for this variable repetition of items at study. And one model that might be able to handle these challenges is the scale independent memory perception and learning model, or SIMPLE. And SIMPLE has several basic assumptions. So first, SIMPLE assumes that each study item is stored in memory as a separate memory trace. So each memory trace is represented in psychological space along a dimension of time, beginning at the time of retrieval and then going back in time. And this time dimension is logarithmically compressed, and this logarithmic compression kind of naturally allows for common observations in free recall, like recency. Also, a memory trace is going to be easier to retrieve the more easily it can be discriminated from other traces within psychological space. The analogy that's used in the SIMPLE paper is the line of telephone poles. So the items in a memory task kind of pass by at a constant rate, just like how telephone poles pass by when you're on a moving train or in a moving car. The crucial point is that as each telephone pole recedes into the distance, it becomes harder and harder to distinguish from the neighboring telephone poles. And in the same way, memory traces become harder and harder to distinguish from each other the farther back they occur in time. So this is how the temporal representation maps to our task. This top panel depicts, it's a one-dimensional depiction of the triadic comparison task as it is completed in real time. Each colored tick mark represents an encounter with an animal name, either as part of a triad read out loud by the clinician, or the animal chosen as the odd one out by the participant. So in this example, the most recently presented triad was giraffe, zebra, and deer. And the participant's odd one out choice for this triad was giraffe. And then after a retention interval, they have the free recall task. The bottom panel shows how SIMPLE represents the memory traces in psychological space after this logarithmic compression. So the ability to successfully recall an animal name, for example, the word giraffe, is going to depend on how easily discriminable that memory trace is from all the others within the psychological space. Okay. The temporal similarity of two memory traces is a function of their separation in time and also the acuity with which they are accessed. So this eta ij is the temporal distance between two memory traces I and j that are encountered at times ti and tj relative to the time of retrieval, and it incorporates this key logarithmic compression assumption. This parameter lambda is a temporal distinctiveness parameter. It represents a participant's memory acuity. The temporal discriminability of an item I to a probe j is calculated via this equation here, where again, more temporally discriminable traces are going to be easier to retrieve. So far I've described the influence of time on memory recall, but SIMPLE also allows for traces to differ on multiple dimensions. So this means that other factors like the semantic similarity between items can affect free recall as well. In free recall data generally, as we just heard, people tend to recall items in semantically related clusters, and we see this pattern in our data as well. So to kind of demonstrate this, here I have all 21 animals used in the study arranged in the circumference of a circle, roughly in order of similarity to each other. Red arrows here represent first order transition probabilities. So these are just the probability of the next recalled word given the most recently recalled word. These are similar to semantic conditional response probabilities. Higher transition probabilities are represented by thicker arrows. Lower transition probabilities are represented by thinner arrows. Transitions that occur around the edge of the circle indicate that the transitions are occurring between semantically similar items, while those going through the center indicate that the transitions are related to something else other than semantics. So this is just for our healthy control group. And here you can see that most of the transitions occur around the edge of the circle between semantically similar items or animals that are semantically similar to each other. So for example, transitions between gorilla, chimpanzee, and monkey are relatively common, while transitions between dissimilar animals like, I don't know, say camel and dog are relatively uncommon. So to create a two-dimensional version of simple, we added semantic similarity data from that triadic comparison task as an additional dimension along with a weight parameter omega to the distance equation. So now the overall similarity of the two traces is a weighted combination of their temporal and their semantic similarities, where again, omega is the emphasis given to temporal similarity. The simple model transforms the retrieval probabilities via a logistic function. And what this does is it just allows study words to be omitted at test. So parameter tau here is the threshold value above which a trace is successfully retrieved. Parameter beta represents the scale or the noisiness of that threshold. So a large beta would indicate that all the traces above the threshold are retrieved and all the traces below it are not. So it becomes kind of like a step function. But a smaller beta value is going to indicate a more gradual transition from low to high retrieval probabilities. So this pi star here represents the probability that probe J will retrieve trace I. Theta I is the probability that a trace I will be retrieved at least once. And as far as I know, previous applications of simple didn't really take into account item repetition or the possibility that multiple traces represent the same item, because that's what happens here. But the extension is pretty straightforward. So the probability that animal A will be retrieved or recalled is just the probability that at least one trace representing that animal is retrieved. So based on our previous work, we do not expect the structure of semantic memory to differ by cognitive impairment. In other words, we expect the access to semantic information to differ by cognitive impairment, but we do not expect the semantic distance itself to differ among groups. So we use a hierarchical model here with group means mu lambda g and mu omega g, where G is the indicator for healthy MCI or dementia groups. In contrast, we assume that the thresholding mechanism does not change with impairment. So we have single means mu beta and mu tau. So these assumptions focus the explanation of changes in free recall performance on the acuity of memory and the use of semantic information, while still allowing for individual differences in the thresholding mechanism. Okay, so these are the modeling results. There's a lot to unpack here. So I will start by discussing descriptive adequacy, which is in this bottom corner here. So we evaluated the descriptive adequacy of the model by comparing the model described retrieval probabilities to the actual rate of recall in the data. This dash line here would indicate a perfect match between the model and the data. So there is some discrepancy here, but generally the model describes the data well. Above that, I have the joint and marginal posterior distributions for mu tau and mu beta, the threshold and the threshold noise. The value of the threshold parameter mu tau is very high. It's very close to 1. And this high threshold indicates that recall was only possible for animal names whose retrieval probabilities were high. The noise parameter beta had more moderate values, so that indicates a gradual and somewhat noisy transition from low to high retrieval probabilities. But the most important and most interesting results are in this panel here, the mu lambda and mu omega parameters, because they tell us how memory acuity and the use of semantic similarity change between the groups. So here we have the results for the healthy MCI and dementia groups. As impairment increases, we see that the values or the distributions for mu lambda move towards smaller and smaller values. So this indicates decreased temporal distinctiveness among the memory traces and just greater confusability overall. The weight parameter mu omega, again, indicates how much weight is placed on temporal versus semantic similarity when they're trying to recall words. A mu omega of 0.5, we can think of as meaning about equal weight is placed on temporal and semantic cues. And what we find is that as groups become more impaired, this omega value increases. They approach larger values, indicating that people with greater cognitive impairment rely more on cues of temporal similarity than semantic similarity relative to controls. So overall, these findings suggest that as impairment increases, first you lose this temporal distinctiveness, you lose this acuity. And that is followed by a loss of access to semantic information. So the loss of both memory acuity and access to useful semantic information jointly seem to cause the worsening recall for patients in the dementia group. So I think I'm over time. In this project, we extended the simple model to account for the free recall of animal names learned incidentally during a triadic comparison task in a real-world clinical data set. We found that people with MCI had lower acuity than healthy controls, but both groups placed roughly equal weight on temporal and semantic cues. People with dementia had both lower acuity and placed much more weight on temporal cues than semantic cues. I'd like to say thanks to the Bayesian Cognitive Modeling Lab at UCI, the folks at the Schenkel Clinic, and the folks at MBIC.